All right, so welcome everyone to today's colloquium. We're lucky to have one of our own, Professor David Goldhaber Gordon, who is going to tell us about quantum simulators and how they can help us understand materials and I guess Hamiltonians. David did his PhD at MIT with Mark Kastner and was the first to look at Kondo physics in semiconductor nanostructures. After that, he moved on, or moved back, I guess I should say, to Harvard as a junior fellow for a couple of years before Stanford was lucky enough to snag him and bring him out here, where he's obviously been ever since. Of course, David has a number of accolades from starting early as a Hertz Fellow, as a graduate student, and continuing on as a, for example, Valley Prize and Macmillan Award as an early faculty member, among other early career awards, and continues to be recognized relatively recently as an APS Fellow for what I would describe as really impressive work across a wide variety of systems, continuing along the same vein in some sense of looking at nanostructures, which we'll hear about today in semiconductor heterostructures, but also doing pioneering work in the field of 2D materials, first just individual monolayers, and then moving on to twisted systems and beyond, and is continuing to push the boundary to try and make these systems as robust and reproducible and large so that they can be technologically relevant. And so I guess I'll let David give the colloquium rather than me, and I'll stop there rather than doing him justice. And, so welcome, and look forward to your talk.
So thanks, Ben, for the very gracious introduction. So I'm speaking without a mic, or I guess actually maybe there's a mic array, but how can people in the back hear? Is it okay? All right. So if that changes, please let me know, because I do enough talking to myself. And today, Ben said that I'm going to tell you how nanostructured systems can be used to understand materials. I intentionally put a question mark there because I think to some extent the jury is out, but I'd like to explore what building experimental realizations of interesting model systems might be able to do for us, and why to do it, and hopefully this can be a conversation. So certainly if there's anything that I've sort of put as central that you don't understand, please don't hesitate to ask along the way. If I think it would be better answered later, I'll flag that. So I'm going to start with something that is familiar to all of us, which is a particle in a box. And when we teach quantum mechanics and teach about a particle in a box, we're doing that because it's effectively a simple example of the real thing that we're trying to get at, which is, for example, a hydrogen atom. And even a hydrogen atom is a simple example of the real thing that we're trying to get at, which is more complicated atoms. But when I was an undergrad and took quantum mechanics, I didn't have that context, and I actually, in retrospect, assumed that we could build a particle in a box, and that was why we did this calculation. And when I realized, as I was exploring what I wanted to do in grad school, when I learned that that was not in fact the case, I at the same time learned that it was just starting to be possible to really build a particle in a box in a somewhat controlled way. And so that was really exciting to me, and it set me on the path that I ended up working on. And so one of the ways to build a particle in a box is to build a set of layers of different materials that can be grown by techniques like molecular beam epitaxy, just fancy ways to build very precise layers. And in this case, electrons are confined to a layer called a quantum well here. In this structure that I've shown you, they're not just confined to a two-dimensional sheet, but they're actually confined also laterally in this pillar. So we get a box that is confined in all directions. And if one looks at the spectrum of levels for this system, particularly looks at the energy to add each successive electron to the system, you can see each of these peaks that shows up, it turns out, in a current that flows through here. Each of these peaks heralds the arrival of one electron. So here we have 0 electrons. The first electron is added. Here's 1 electron, then 2, 3, 4, and so on. And one interesting and striking thing here is that if you look at the spacing between these peaks, the energy needed to add each successive electron, you see that there are peaks at 2, 4, 6, 9, 12, 16, particular values. And those particular values may not ring a bell for you, but if you look particularly at the 2, 6, and 12, which are some of the big ones, there seems to be a certain regularity to them. Of course, we only have 3 numbers, but these are in fact the, in atoms, you know that you have shells that can take 1, 3, 5 electrons plus doubling that with spin. These are the numbers for an atom if it lived in 2D and if it lived in a harmonic oscillator potential instead of in a Coulomb potential. And it turns out that that's effectively, a harmonic oscillator is effectively what's produced here. So here we have something that can be really thought of as an artificial atom if only the world were two-dimensional and interactions were a little bit different. So, having shown that one example of building a realization of some particular interesting Hamiltonian, which is electrons in a cylindrically symmetric harmonic oscillator potential in 2D, let's think more broadly about if we were to realize simplified models, why might we do it? What might we get out of it? And so I don't know how many people in the audience have ever watched or heard of the show Family Feud on TV? How many people have heard of TV? No. So for those of you under the age of 50, Family Feud was a rather corny show where 2 teams competed to guess what might be the top answers to a certain survey question that might have been asked of a lot of people in the US. So in this case, so to liven things up, I'm going to try something a little bit new and play a game with you, a version of Family Feud, if you will. But it's, I'm going to, instead of thinking about what are some concepts commonly associated with vampires, for which garlic or bats or steaks might come up, instead we're going to think about why would one possibly want to create experimental realization of model systems, particularly quantum systems. And instead of a survey, this is just my own idiosyncratic views on the subject of, that I've developed over the last few decades. But does anyone want to throw out a reason that one might want to build a relatively simple model quantum system?
Solve the Hubbard model.
All right. So to solve the Hubbard model, I would say I'd put that under computing power. Can you do something that a classical computer isn't good at? And Lenny pointed at this because many people have been advertising that they're going to solve the Hubbard model. Well, we can get to that later, what the Hubbard model is, but solve the Hubbard model and therefore finally understand the most important and stubborn problem in condensed matter physics today, why high temperature superconductors work the way they do. It's not clear. It's not clear that solving the Hubbard model will do that. It's not clear that we can solve the Hubbard model with methods that have been brought forth, but that's definitely one of the motivations. Any other reasons if you can't solve the Hubbard model?
You can get Lagrange in
Get more grants. So maybe it's my flaw, Daniel, but I didn't put that on the list. These are long, hard experiments, and it doesn't seem to. If I were trying to get grants, it wouldn't be quite the way I do it.
I got an idea.
Yes.
Because it feels so good when you stop.
Yes, I found that when I keep hitting myself with a hammer, and
Discover new phenomena.
to discover new phenomena, I think that I'm going to put under well, I think I will just go through them because I think that the mapping is sorry. I'm trying to. All right. I guess that one aspect of my tool didn't work. I just built this today. So all right. So I would say the ones I came up with were delight. There's something that it's to me delightful that you can build an atom as it would be in 2 dimensions, and that it can just behave in that beautiful, elegant way. It's maybe a more deep delight if there's some really counterintuitive prediction, and the theory, you can work it out in the theory. There's no problem with computational resources, but it's really counterintuitive. And if you can build the realization of the system and see that it works that way, to me, that's satisfying. I really like looking at, finding some prediction that doesn't make sense to me. I don't really believe that it should be that way, and then either seeing that it's right or that it's wrong. Intuition, so we'll get to this in the example that I'm going to give next, but maybe you have some model and you can do calculations on it, but you don't have some overall grasp of how it should behave in different regimes. Can you get a sense of that? Quantitative tests, maybe it's something that you can do. You can do cutting edge computation on a classical computer, but do you really know that the computation is right for the problem that you're working on? I find it satisfying to be able to compare to an experiment in great detail. And finally, there's the computing power, where there's something you just can't do on a classical computer to the extent that you'd want to. So I'm contractually obligated to look at this through the lens of this particular phenomenon of Kondo physics, as Ben alluded to. And so let me tell you just one thing about the Kondo effect, or a few things about the Kondo effect. It's a canonical example of many-body physics happening in the solid state. So if you have a local moment, say a single magnetic atom, so an atom, say, of iron in a chunk of copper, then does it retain a spin? Does it continue to have a spin even though it's immersed in many other electrons? And it turns out that it's complicated. So there's a new energy scale that emerges, the Kondo temperature, which is related to but not directly appearing in the Hamiltonian. And at temperatures below that, the local spin is screened. The electrons around it form a singlet with it, and there's no spin left over. But at high temperatures, the spin is free. And so it turns out that this describes the low energy physics of what's called the Anderson impurity model, which I'll tell you a little more about as we go on. But it's basically a box that can hold 0, 1, or 2 particles, and they interact with each other. And electrons can jump in or out of the box. So how might we apply the idea of building a model system to get intuition in this case? So this is a problem that the phenomenon of the Kondo effect was first observed in the 1930s in what was then thought to be pure gold. Turned out that people had drawn the gold wires through a steel die and had gotten a little bit of iron in it. It took 50 years to figure out what was going on. Miriam Sarachik, who recently passed away, was instrumental in identifying that it was associated with magnetic impurities, that this wasn't pure gold. But by the 1980s, I would say there was at least a small set of theorists who really understood this quite well. But the broader community maybe didn't have such a great intuition for how the Kondo effect behaved. And when I was starting grad school, one of the possible things that I could choose to work on was trying to build something based on these quantum dots, artificial atoms, to try to realize the Kondo effect. And together with Mark Kastner, who was my advisor at that time, and others, I set out to do that. I don't think any of us believed that it would work, but it turns out that it did. So what are we doing? There's a lot on this slide, but we use a slightly different technology for building this artificial atom. We have electrons sitting in a 2D layer, a quantum well that is below the surface of the screen here. And then on the surface, we put a set of metal electrodes in the shape of a box. We put a negative voltage on those electrodes, so they deplete electrons underneath them, but leave a little puddle in here, and then bigger reservoirs on the two sides. So if we have an odd number of electrons on this quantum dot or artificial atom, the electrons could all pair off, but there's still going to be one left over, and so this looks like a magnetic atom, if we're thinking of it as an artificial atom. If we allow strong tunneling to the reservoirs, then we can't think of it as an isolated artificial atom. Instead, it's more like an impurity atom in a metal. So if we put that all together, we now have a magnetic impurity, an artificial magnetic impurity in a metal. And here I'm drawing just in energy space and one cut in real space. We have the reservoirs of electrons, and then our box where we have only certain discrete states. We could put one electron in, we could put two electrons in, and we can tune the number of electrons in the system with one of the nearby electrode voltages. And here I'm showing you tuning that and tuning the voltage applied across the system from one reservoir to the other. I'm not trying to give an understanding of everything here, but in this region, in this diamond-shaped region, we have an odd number of electrons, let's say 21. And so normally, if you looked at that old artificial atom that I showed you, that should be a situation where no current flows through the system. But in fact, this color scale is showing the conductance, and in fact, there's a reasonably high conductance in this region where there should be none. And this is because of the Kondo effect. And it comes about because even though we couldn't put one electron stably onto the system, it has, say, 21 electrons, it doesn't want 22, we could temporarily put an extra electron on and then tunnel off, and you can see that you have this process where the spin on the site flips, and this and higher order processes turn out to give rise to the Kondo effect and represent the screening of the reservoir by the reservoir of this local moment. And it shows up in this enhanced conductance, which is an enhanced density of states right near the Fermi level, right near the level to which electrons are filled. So this was sort of a dramatic qualitative demonstration, something that looked very different from what had been seen before. But it wasn't yet quantitative, and I decided, all right, let's get greedy and see, can we check whether this works quantitatively? So I mentioned this Kondo temperature, that it's not simply appearing in the Hamiltonian, but it's related. It's supposed to be related based on some simple scaling theory or some crude scaling theory. It's supposed to be related exponentially to the bare parameters of the Hamiltonian, where U is the energy for the charging energy, the extra energy to put an extra electron on the system. Gamma is the rate of tunneling in and out, and epsilon 0 is the depth of the level below the Fermi level. So this scaling theory just sat there for quite a while, because if you have one atom of iron, if you have, let's say, a part per million of iron in copper, you can make a chunk of copper with a tiny sprinkling of iron, you can't adjust just the tunneling rate. You can't adjust just the depth of the level below the Fermi level. You could replace the iron with cobalt, or you could put pressure on and change a number of things at the same time, but you can't really fine-tune one of these parameters. But here in this model system, we can tune each of those parameters and we can measure those parameters precisely. And so what's captured in this plot is the result of a lot of analysis, but we extracted the Kondo temperature as we tuned the depth of the level below the Fermi level, and found that this is on a semi-log scale. This is depth of level, and here's a log scale for Kondo temperature, and indeed, it's falling exponentially. All right, it's not over a huge range because, unfortunately, my order for a zero temperature cryostat was perpetually delayed. But it's exponentially falling, and that was really quite exciting. And then I said, all right, let's get greedier still. Let's look at what is the prefactor in the exponent. It's supposed to be pi times this combination of parameters of the system. If we treated this measurement as an extraction of the value of pi, we'd get 3.05. The ancient Egyptians did better, but I was quite impressed that it was that close. And by this point, the theorists involved, both those who Duncan Haldane, who was responsible for this theory, and other theorists said, yeah, I wouldn't have expected it to be that close. So I said, how about this prefactor in front of the exponentiated part? And people said, oh, that's just an effective bandwidth. It's very rough, probably within an order of magnitude or so. It turned out to be within 10 or 20%. It's the geometric mean of two of the quantities that appear in the Hamiltonian. And so this really set me on a path of saying, I think we can maybe be unreasonably greedy about asking for tight quantitative comparisons between these simple model systems and between the simple models that we're trying to get at and the experiment. So another example of a quantitative comparison is that in this realization of the Kondo effect, it is expected that not only is the conductance for an odd number of electrons, not only is it not zero, but it actually can be exceedingly high. So it should be able to be as much as 2e squared over h. And that's the conductance of a perfect 1D wire in which both electron spins can transmit simultaneously, which is really counterintuitive, because if you think of a box of electrons, when there's an electron on the box, it should block an electron of the other spin from coming through, and so it should never be possible, it seems, to get more than 1e squared over h, and even that should be pretty tough to get. And yet here we're almost at 2e squared over h, the conductance of a perfect 1D wire. This was work from the Delft group of Leo Kauenhofen. So let's think about how this can maybe relate to trying to understand materials. So if we want to build tools to understand materials, then we have some different things that we can bring to bear. We can do so-called first principles calculations, where we try to calculate based on just the structure of the system, and depends quite how religious you are about this, how many assumptions you're willing to make, but basically trying to really brute force calculate how electrons in a certain lattice should behave, maybe even how the lattice should relax. And this allows for direct, hopefully quantitative comparison between experiment and theory, and it's turned out that in the realm of 2D materials especially, this has been extremely fruitful, and it's been possible to do quite quantitative calculations of band structure. But it's hard to bring in interactions in a controlled way. So if you pretend that all the electrons don't talk to each other, you're fine, and it's miraculous and wonderful that allows us to understand a lot of things. But But if you need to deal with interactions among the electrons, then you really have to make your model simpler in some way. And so a lot of what we do in condensed matter is engaging with effective models with Hamiltonians. And certainly we're never trying to solve a Hamiltonian with 10 to the 23 electrons or more, which is what you should in principle be doing if you were trying to brute force calculate the behavior of a chunk of material. Instead, you write a model that you think captures the essence of what's going on in the more complicated system. But even those effective models sometimes cannot be actually solved with our computers. And this was, in my abstract, I talked about Feynman's philosophy on what quantum is good for in computing. And he imagined that, that calculating the behavior of quantum systems is something that you could probably do pretty well with quantum systems. And so, so that was the idea of quantum simulation really goes all the way back to him, and he felt, I think, more strongly about that than about what's now known as general purpose quantum computing that's much more popular. So, so if we try to model quantum systems by nanopatterning electronic structures, there are advantages of this. You can design your structure, you can draw whatever you want, and then build it in the nanofab, and often that means you can design a Hamiltonian that's interesting. You can measure and tune often all of the key parameters of the system. You can compare to computation. So if you take the best available classical computation and you take a small enough or simple enough nanostructure, you can compare the two and see, as I showed you in the case of Kondo effect, do they really lie on top of each other? You can interrogate locally what's happening on different sites by different methods. And by the way, when I'm saying pro and con, part of this is in comparison to the elephant in the room, which is cold atoms, because quantum simulation has become very popular for in atomic physics, with often the advertised argument being that we'll solve the Hubbard model. There are some great advantages of the cold atom systems, but I think the solid state systems have some advantages also in terms of really being able to control a smaller system and control everything about it, as opposed to making something very large and uniform. But on the con side, in the solid state, it can be hard to make a big system where every site is identical, whereas you can hope to get closer to that in an optical lattice that holds atoms. And of course, every atom, at least a given isotope, is identical to the same, to any one of the same atom elsewhere. So in solid state, it can be hard to scale to many sites and make them identical, which might make you think it's going to be hard to connect to real materials. And there might be only certain Hamiltonians that you can access. So I'm going to go through these various points. Designing the Hamiltonian. So this is a simple double quantum dot, 2 boxes of electrons. And actually, we're not allowing tunneling between the two. We pinch off this connection so strongly that electrons can't get across, but they still feel each other through their fringe electric fields. And so the Hamiltonian here, you don't need to dig into it in great detail, but you have electrons in each reservoir, electrons on the site and their energy levels. If there are 2 electrons on the site, on a given site, they have a repulsion between the two, and then there are tunneling terms that allow you to go between each site and its reservoirs. And finally, after 2 copies of that, we're going to add on just a simple Coulomb interaction, interaction between the 2 sites so that one of them feels the other when you add an electron to the other. And so we could then think about, in this context, measuring and tuning the key parameters. So if we change these 2 gate voltages, they're known as plunger gates. I think Charlie Marcus, who coined a lot of good phrases, I think he was the one who named these plunger gates, because you can imagine squeezing down or opening up these little boxes. As you tune one gate, you add electrons to one site. Tune the other gate, you add electrons to the other site. the boundaries between these regions are a little more complicated than just straight vertical and horizontal lines because of cross capacitances and interactions between the two sites, but let's not get into that too much right now. So we could label these different regions by their occupancy of each site, and then we could focus in on this region where we can have an extra electron. It can either sit on the left site or on the right site. And right along this dotted line, the two are degenerate with each other. And so if we do the experiment, this is what it looks like. So you can see that it bears quite a bit of resemblance to the cartoon picture that I drew for you there. And what that means is we really understand what's going on, and we can extract the parameters of the system. We can extract the electron temperature, the tunneling rates, the on-site charging energy, the inter-site charging energy. So we can really get control of that. Some of them we can tune, others we can just measure precisely. So now if we want to compare to computation, I'm not going to get into what we did with that particular double dot system. It was a variant of Kondo physics, but here are some examples of what people around the world have done in this sort of space. So one example is having 4 sites and 3 electrons on them, and there's a famous sort of cute idea from a theorist named Nagaoka that even if you had a lattice of sites and tunneling between them, sort of a Hubbard-type model, and you had all the sites filled, it should be antiferromagnetic, so we should have a tendency of alternating spins. But if you take one electron out, then it should become a ferromagnet. And I can talk with people afterwards about why that is, but it seems obvious that nothing should actually change if you take one electron out of millions, but the idea was very clever and elegant, and a group was able to demonstrate that in just a 4-site system, that if you took one electron out, that you get all the ferromagnetic correlations, the spins align with each other. Another example was a variant of the Kondo effect that was actually, among others, studied beautifully by our colleague Steve Kivelson, and this is a system that it turns out my group was able to build for the first time. It was not clear whether there was any case that this happened in nature or in bulk materials, though there have been some proposals for it. And we were also able to see a quantum phase transition, a switch between two distinct many-body states as we tune the parameters of the system. There was elegant work from a group in Saclay, Frederic Pierre's group, on building further extensions of this sort of Kondo effect that I had considered just curiosities, but he showed that you could really get some quite remarkable things out of them. And then there's work from Delft on the so-called Fermi-Hubbard model, just a few sites, and allowing hopping between the sites and what are the ground states. And this is a toy example with just a few sites. But even that was a tour de force. So we can locally probe each of these sites. So we can either, in the case of these 2 sites that are coupled capacitively to each other, we could measure current through each of them separately and probe them separately. Or we could have some capacitive sensor that can tell something about when electrons jump on and off the different sites, and we could have multiple sensors that could detect the different sites, or one sensor, and we can see by its signal which site an electron is going on to. So this is hard to scale to many sites. Why is that? It's because it's very hard to make one site exactly the same as another. Even with very excellent electron beam lithography, drawing these fine features, it's always going to be a little different. There's a little roughness. There's an impurity in one place versus another, just an atom in and out of place. And so each site is going to be a little different. And you could think, all right, let's just tune them to be the same. You could probably tune them so that you have the same number of electrons on the sites and even the same energy of a level. But the wave function there will have different tails, and the next wave function up will have different spacing. It's very hard to make that uniform over a large number of sites. And there are certain Hamiltonians that come out naturally, and we can't necessarily build every one that we might want. And so there's some things that I've been wanting to do for a long time and couldn't think of a way to do them. So there's a new system that emerged. I say new in quotes because it was actually proposed by Kostya Matveyev, a theorist, decades ago. But the idea is that you have a metal grain. So unlike a semiconductor system that has just a few quantum levels, this metal grain has such a high density of states that there will always be many levels occupied near the Fermi energy. And you don't want to worry about just having a particular one occupied. And so the state of the grain is going to be determined by how many electrons are on it. And we could tune it maybe so that we could tune it with the nearby electrodes so that we could come close to degeneracy between two different charge states. And then if we allow tunneling to a reservoir, tunneling through a very perfect 1D channel, then it turns out this should show Kondo physics. I'm not going to go through the details of why this is. I'm happy to talk with people offline. But let me just give you one sense of it, which is that the two charge states here play the role of spin. People have gotten used to with qubits that you can have a two-level system and it can be almost anything. So here, instead of spin, it's the two charge states. It's a little more subtle. What is the screening of those effective spins? But again, I'm happy to talk with people later. So the requirements for this are if you want to really build this, people tried in the 90s and failed. You want a large charging energy, so a very small metal grain. You want precise control of the tunnel couplings. Normally, if you have a metal connected to some other conductor, you'll be tunneling through an oxide, and that oxide will have many poorly transmitting channels. But in Matveyev's model, you really want to have one channel that has a transmission between 0 and 1. So you want to have that situation. You want a large density of states in the grain. And it turns out you can't achieve these very well if you restrict yourself to just semiconductors to hold the electrons or just metals. But Frédéric Pierre at Saclay, who I mentioned before, had a clever idea for how to get around this. So he said, let's use a metal for the island, but let's couple to it with a semiconductor so that we can have a narrow constriction and we can pinch that off to allow transmission, whatever transmission we want. And then he added one more clever thing, which was to say, in the semiconductor, we'll use quantum Hall edge modes so that you have a very perfectly one-directional motion along, let's say here, counterclockwise, and then it reaches this constriction and it can either transmit or reflect. And it turns out that allows very fine tuning of the system. It removes the real spin from the problem because we're at high magnetic field, so we don't have to worry about having both spin up and spin down here, which would complicate the situation. And what he showed in this three-channel case, where there are three arms that are trying to screen the local spin, is that there are three different fixed points, three different many-body states that you can go to, and these arrows that you see are things that are derived from his experimental measurements in terms of what is the flow of the system as you go to lower temperatures, lower energies. And you see that there are arrows that point to this this point here, which is called an intermediate coupling fixed point. There are also areas that point away. This is not a very stable fixed point. There are arrows that point to this, this fixed point where there's zero conductance through the system. I'm not going to get into all the details of it, but what I find really striking about this is many of you may have learned about renormalization group. This is the first time I've seen an experiment that effectively visualized a renormalization group flow between fixed points. So now let's get to finally the experiments that my group has been working on over the last 5 or 6 years, and this was, on seeing Frédéric Pierre's system, I said, now finally there's something that I think we could clone and make effectively identical copies of it, because no longer do we need to worry about the detailed energy levels of this box. Effectively, all that matters is the size of the box, its basic geometry that will determine its capacitance and therefore its charging energy, and then we can tune the tunneling rates. And so I was excited about the idea that we could scale this up to a chain of magnetic sites that could each be coupled to its neighbors, and that we could start to really connect to real materials. So it turned out that after we had started working on this, but before we had really gotten fully into the experiments, we spoke with a theorist, Andrew Mitchell, and he said, you've been thinking that this is like the traditional model of two magnetic sites that are coupled to each other and coupled to leads, the two-impurity Kondo Hamiltonian that's used to try to understand a class of materials called heavy fermions or Kondo lattices. But actually that's not the Hamiltonian you have. It's actually much richer and more exciting. And I was crestfallen, because I had been trying for years to build this particular Hamiltonian, but over time I've come to, first of all, we can't change it, but also I've come to appreciate Andrew's point that this is actually a much more interesting Hamiltonian, where the coupling between the two sites is actually itself a Kondo type coupling, not a simple spin-dot-spin coupling, but there's also additional tunneling of fermions involved. So that's for the cognoscenti. So when we make measurements on this system, and in the middle column, we have the results of cutting-edge numerical renormalization group calculations. These are done on supercomputers, and Andrew Mitchell had a lot of access and needed to use weeks of supercomputer time in order to calculate these. And he said to us, if you had one more site, not 2 sites, but 3 sites, or if you attached one more lead, if you weren't trying to just have 1 lead on each site, but 2 leads on each site, it would be totally beyond the capacity of what he could do. So I'm not going to guarantee that if Google or Amazon decided to throw their collective might at it, that they couldn't do 3 sites, but 4 is probably right out. So this is really, even though it's a small system, it's pushing classical computation that is good for really low energy many-body physics to its very limits. And here are calculations of conductance you might expect through the system through these 2 sites in series, as we're doing the same thing that I showed you before, adding electrons to one site, adding electrons to the other site, and this is where we're near an extra electron that can sit on either side. And here are the data for the same parameter values, and we're taking strong coupling and weaker coupling, and you can see there's quite a nice match between the two. We can also, with the computation, go places we simply can't with experiment. We can't get as cold as 2 milledegrees above absolute zero, even though Doug Osheroff did that for his discovery of superfluidity in helium-3. It turns out to be much more challenging to get electrons that cold than helium, but it can also give you some intuition going to places that the experiment can't. Importantly, we can really just directly compare almost all the parameters across here. So it's with one exception, we're not saying all right, we're going to pick the parameters in the theory that make the best match to the experiment. No, we can read off all the parameters in the experiment, tell the theorist, plug these into your machine, and give out the result. The one exception is that we deal with transmission probabilities for our tunneling, and they deal with a J, a sort of effective coupling across there, and it's not totally clear what the mapping between those is, except that it should be monotonic, but that's the one small exception, so we're using 0.35 for J instead of 0.38 for tau. So I'd like to say that pictures like that are beautiful, they can give intuition, but color plots can hide a multitude of sins. I can pretend that things look like each other, and so we really should look quantitatively at line cuts through this. And here we're comparing experiment to theory, and one thing that you can see is that as you change the coupling between the two sites through these many steps, that you end up with two peaks that end up moving apart from each other as you increase the coupling. And that's sort of qualitatively matched here, and there's reasonable quantitative match in terms of the levels of conductances. So now let's try to ask about the real physics happening. So one thing that you might look at is if you're sitting in the experiment and you're sitting at a certain coupling to the leads, and then you change the coupling between the two sites. When you think about it, you might expect that when the coupling between the two sites is 0, you can't get any electrons through. And when the coupling is too strong, then the two sites bind together strongly and you can't get electrons onto or off. It forms a local singlet. It doesn't couple to the leads. So you might expect that there would be a non-monotonic behavior and that the conductance through the two sites in series would reach a maximum when the coupling between them has some intermediate value, and probably that there's the higher the coupling to the leads, the higher the intermediate value you would need to maximize the overall transmission. And indeed, this is sort of true, that as the coupling to the leads gets stronger and stronger, the coupling that gives you the strongest transmission through it is monotonically related to that. So we can try to get all sorts of things like what's the behavior at high temperature, what's the behavior at low temperature when you break a symmetry in the system. So those of you who are in particle physics are familiar with the fact that at high energies we have 4 types of photons, but at low energies the W's and Z's look very different from photons. Similarly, when we get to very low temperatures, we can actually and we're not exactly at our quantum critical point, which is a particular point in this diagram, then we can see that we're not there, and we drop into a different, less interesting state. So I think that in the interest of time, I'm going to just wave my hands at this. We can pick a point in this parameter space of gate voltages where we think we're completely at a quantum critical point, or very, very close to it, and then we can move away from that by tuning gate voltages. And there's a scaling theory for how tuning away in gate voltage should change the effective energy scale below which we see that the symmetry is broken. And if we use that, we can see that we can plot this scale T star, this effective energy scale, and plot conductance. And for a bunch of different data, we can plot them all in the same plot, and you see that to a reasonable extent, they fall together on a calculated line. And then you can also see that they deviate from it. It turns out that deviation is because we're cutting along this line, and when you go too far, you actually come close to the next pair of peaks where you can add more electrons. And so if you make a correction for this that other theorists suggested, then you find that actually it falls along that line. It even does somewhat better if you move away from this special point in another direction. And so I think that I'd like now to just take stock of where we are. So, so what do we have? We have two sites. Each of them has an effective spin. They're coupled together in some rather exotic way that has a quantum critical point associated with it, where you can either be more strongly coupled between the two sites or more strongly coupled each site to its reservoir. But if you tune it just right, those will, the system will not be able to choose between those, and it will be in a really interesting fluctuating state, so-called quantum critical point. Where does that get us? So my motivation in trying to build this system in the first place was in part to try to understand some bulk material, or to get some intuition for some bulk material. And one type of material is one that has an array of effective magnetic sites embedded in a metal, and these sites are coupled to each other and coupled to the metal, and it can result in a set of bands that are very flat, where energy is almost independent of momentum, and as a result, it looks like the objects that move through this are very heavy. They don't have a lot of kinetic energy, and so these are called heavy fermion systems. And so many heavy fermion systems occur in these sorts of so-called Kondo lattices. And I thought it could be interesting to understand those, and so trying to look at the quantum critical point between each local site being screened by its reservoir versus all the local sites locking into order seemed like something we might be able to access in this artificial system. If we want to do that, we need to scale up to many sites. And to do that, we're going to have to do some hard engineering. And so there are some technical requirements. I guess, sorry, somehow this skipped the one that I wanted. All right, what happened? Yeah, I don't know. All right, so we need to be able to tune all of these couplings. We need to be able to build sites that are all the same as each other. We need to get very good transparency between the metal and semiconductor, and we need to get very small sites so that they can have high charging energy, because once we get up toward the charging energy of a site, all this physics breaks down. And so it turns out that over the last few years, my group has been working on using a different material system to make smaller islands to push up the charging energy, and has been able to see we can get good quantum Hall effect in that system. We can get some really beautiful quantum point contacts that have tunable transmission. We can get tiny metal islands with very good transparency. This was actually the first selling point for that material system, that I could see that we'd be able to make very small metal islands, which wasn't possible in the other material. And in fact, we've made little islands, little hybrid metal semiconductor islands that actually show Coulomb blockade. And so we've sort of built the necessary things, although trying to do this in an academic fab is really thankless, because at Stanford, it's wonderful that we have great tools and they're very flexible, but it means that everyone else can put whatever material they want to into the system, and one person's sample is another person's dirt. And so it may be that to move on further, we might end up moving toward working with industrial fabs, and it's possible that some of the developments in quantum computing could facilitate that. So I'd like to acknowledge the people who made this happen. This is one of those experiments that I didn't see anything that obviously shouldn't work, but I also didn't believe that it was going to work. It was just, there were too many things that had to happen, but I've had enough experience in my career of things that I didn't believe they were all going to work, and then one by one we checked the boxes that I said, all right, I feel reasonably okay setting out on this odyssey. But it was a real challenge, and Lucas Peters, a student of mine whose background was in string theory, and took on the challenge and was joined by Winston Paus, who's just in the process of graduating now. And at the end of that odyssey, they got the results that I've showed you for quantum critical behavior. the baton was passed to Connie Shu and Praveen Sriram, who have taken this to this new material system, indium arsenide, which brings its own substantial challenges, but they've really shown that they can succeed on all of the key aspects to build this there. And so in particular, they've pushed up the energy scale for the charging in that by a factor of a few, which should make it much easier to study this. Andrew Mitchell is the theorist who had key insights and did computations. Ulf Genzer and Antonella Cavana grew the sample. And Mark Kastner, my former PhD advisor, I'm really blessed that he's in retirement, come to join and work with me here. And he's like a second advisor to many of my students and also a wonderful discussion partner. Andrew Keller did the double quantum dot work and really set the stage for a lot of this. And the funding support for this work has been primarily from DOE, from the through the Stanford Institute for Materials and Energy Sciences, and also especially for a lot of the cryostat and other electronics, the Gordon and Betty Moore Foundation's EPICS program. And I'd just like to leave you with an outlook with some wild things. I'm not going to dig into them in detail, but if you take seriously the calculations and analysis that have been done theoretically of this, the excitations of these systems should look like Majoranas or even more exotic extensions of them. And so this could be a quite different experimental model where we could test and manipulate Majoranas and do things, and some of you may have heard of topological quantum computation and braiding, and those are things that should be possible in this system once we have a third site. But we can also go in the direction of trying to make models that may have connection to bulk materials, and so scaling up arrays to try to understand the coherence in Kondo lattices, which is a persistent puzzle, or making use of the fact that we can see effects of boundaries in this system. We might be able to study topological edge states. So I think we're in a really exciting time. There's a lot of challenging engineering ahead, but also I think for the first time we can see that in solid state with fermions, we can actually build scalable quantum simulations. So I'd be happy to take questions if people have them. Yes. Right.
Just sort of looking with not a lot of knowledge at the geometry of the two body systems made there. Is there a limitation in whether or not could you actually build a fully 2D sheet with many rows and many columns?
Yeah, that's a very perceptive question. So the question was, all right, it's a lot to squeeze in two of these. Can we go to a full two-dimensional array? So you can probably imagine how we could squeeze in a third. It's challenging, but we can fit everything in. We could also do a 1D array because there's room to get in on top and bottom there. We could probably even do a two-leg ladder, so a 1D array, but with two chains next to each other and tunneling between them. We can still get to it from each side. If you go beyond that, you have to have a way to connect to the interior, to electrodes in the interior. In the semiconductor world, so if we're talking about working with industrial fabs, the computer chips you have in your computer, they are not contacted just from the edge. They have direct vias to contact the full area of it, and even then, it's hard to get enough lines out. But so the technology for making internal contacts exists, but it's ultra painful with academic fab approaches, and so I wouldn't attempt that without an industrial fab. Yes?
For this work with the critical point, what is the symmetry being broken?
So that's a good question. And so the question was, what is the symmetry being broken with the critical point? And I'm just going to go to here. This is probably the best place to look at it. So it turns out that this critical point, there are two perturbations that one can make that are so-called relevant perturbations. One of them is moving away from, well, maybe the easiest way is to, or you can think of, yeah, let's look at this plot. So if we move away from, we could move away from having it equally good to have an electron on the left or an electron on the right. So that would be one version of breaking that symmetry. We could move away in this direction, which would be favoring having an extra electron on one of the sites instead of being fluctuating between two values. And then this symmetry is the coupling between the sites perfectly matched to the coupling to the leads, so that you have to be perfectly matched to be at the critical point. If you have too much coupling between the sites or too little, then you'll move away. And something really, interesting and non-trivial here is that these two add together. These three types of perturbations add together, with each one of them raised to the 3/2 power, and that's not standard. It's and I'm not going to pretend that our measurements prove that the power is 3/2, but I would say it's not 1 and it doesn't match 2 very well, and further experiments, yeah, we'd have to dig in more for how close is the comparison to the theory. But does that answer what was the symmetry breaking?
I guess kind of. There's not like a universality class that puts in?
There is, but there's nothing else known that is in that universality class. So that's what excited Andrew Mitchell so much when he introduced this. Yes?
Yeah, let me answer this. That there is no symmetry breaking in the usual sense, which is an order parameter turning on.
Right, sorry.
This is a
yes.
switching between what amount to molecular states of the site. And the renormalization is not coming from an order parameter. It's being borrowed from the metallic nature of the leads. And so, yes, it's not, it's a unique set of low energy behaviors that don't correspond to anything that we have with conventional order parameters.
Thank you.
So maybe in closing, just to wrap that up, this we built something that is a realization of something that's it's a quite interesting Hamiltonian that has new properties. It's perhaps a little bit aesthetically unsatisfying to me that it's not mapping to a classic model that's in condensed matter physics. But on the other hand, it may turn out to give a better set of insights into the Kondo lattice problem than the old two-impurity Kondo model, because it is possible to, in this system, to over multiple sites have electrons delocalized over multiple sites, which would never be possible in the original model, where it's just a standard antiferromagnetic coupling between sites. So my hope is that this could give insight into particular condensed matter physics contexts, but I think also it might be a way to ask how far can we push classical computation and to benchmark it and extend beyond what's been done on a classical computer. So with that, thank you. So Lenny, I didn't end up doing Hubbard, but
Oh, it was half a joke.
yes, no, I know.